Good afternoon. This is the third lecture. And since I'm wearing a mask, some of you may not have any idea who this person is, because I'm from astrophysics, where actually Sara got her degree. My name is Dimitar Sassilov. And I was lucky enough to have Sara as my first graduate student, the very first. And so we had a great time, I think, at least I had a great time as a mentor, writing papers and doing research. And we still have great time exchanging students nowadays and working on projects. But one thing which I want to say in introducing her today is that Sara always had a knack for the big vision, really the breathtaking vision. And the last one, today's lecture, is indeed the one that will take your breath away. So on to the search for another Earth. Sara.
Wonderful. Thank you so much, Dimitar. It's great to be here. And I want to say that during my visit, I've really enjoyed meeting the very enthusiastic students. So thank you again. So today I'm here to talk about the search for another Earth. And by that, I literally mean a true Earth twin, which I'll define that in a moment. So I'm going to give you an introduction about the other Earth, the possibilities that we're considering today that we, for a few decades, have been working very hard on, and then I'll talk about the future. So believe it or not, we have a real image of Earth as an exoplanet. It's not the beautiful Apollo image of Earth, but it's the one on your right, which was taken by the Voyager 1 spacecraft at 4 billion miles away. And what you see there is a pale blue dot. See it? It's kind of hard to see, actually. And this pale blue dot is surrounded by this kind of corridor of pink, which is actually light scattering in the camera optics. But I really like it because to me it resembles our exozodiacal dust, our zodiacal dust rather. Our asteroids collide and they give off dust which reflects in the red. So when the time comes and we get our beautiful pale blue dot image of another Earth, it will actually be contaminated by background dust if the other planetary system also has an asteroid belt like we do. So believe it or not, we also have a very beautiful spectrum of our planet Earth as an exoplanet. And if you don't know how this is taken, the mystery is for you to think about it. There's a hint on here, and I'll be explaining that in my next slide. But in the meantime, I wanted to walk you through this spectrum. It's showing you relative reflectance, so these units are somewhat meaningless. It's normalized to 1. And this is wavelength in microns. So visible wavelengths are here, near infrared is here on the right. And going from left to right, you can see Rayleigh scattering. So if we saw Earth as an exoplanet, we would know that Earth appears blue at visible wavelengths due to Rayleigh scattering from our gas molecules in our atmosphere. There's a big broad feature of ozone here, labeled by O3. We also see other features of oxygen. That's, for our own Earth anyway, our best biosignature gas, as I talked about in the first 2 lectures. Without life and photosynthetic bacteria, we would have virtually no oxygen in our atmosphere, yet it's here to 20% by volume. But if you take a step back, what's the most noticeable features here? It's actually water vapor, H2O, all these. And water vapor is, in fact, Earth's most biggest greenhouse gas. We don't hear about it in the news typically because we're not changing the water vapor content of our atmosphere. Water vapor is a fantastic thing that we really want to see on a rocky planet far away because it should mean that there's a liquid water ocean, an ocean reservoir, because water will be photodissociated by ultraviolet radiation from the host star, and hydrogen would escape to space. So if there's water vapor, we are going to take that as an indicator there's a water ocean. All life as we know it needs water, so that would be a big achievement. So also there's some very small features of carbon dioxide here, some methane showing up right at the edge of this diagram. So it would be spectacular if the day would come when we get a spectrum like this. We don't have one yet. Towards the end of my talk, I'll show you a simulated version. Anyone want to guess how we got this spectrum of Earth? Got it from the moon, from the so-called Earthshine. I got this textbook figure to explain it to you, but essentially this is showing you our sunlight hits our Earth, but our sun also lights up the moon, but sunlight that hits the Earth, Earthshine, sunlight hits Earth, it lights up that dark part of the moon that's facing us, and that comes back to Earth. So I really want you to try to look for this. I can't remember if we're at new moon. We're definitely approaching new moon if we're not there right now. So sometime like in the next week or so, you need to look outside just after sunset at the crescent moon, and you might see that. The moon is such a poor reflector, it jumbles all the rays coming from Earth, and if you can look at part of this and calibrate out the moon by looking at the bright side of the moon, you can get a spectrum of Earth actually. So this doesn't show you where the rays go back to, but you have to be on the night part of our planet. And people have studied Earthshine. There was a group that studied it for a decade, looking to see if the brightness of Earth changed over that time, that if we had cloud increase or what have you. And I'll never forget when the person on this project told me if he watched Earthshine, he said he could see Asia rising. Literally meaning that from California, he could see it because the ocean is very dark and land is much brighter. So as the Earth was rotating, he actually could see that. Also, if it's wintertime, I'm not sure if you're actually going to do this. I'm a little over-enthusiastic about Earthshine, but sometimes it's so bright. And that means the people to the west of you have a lot of snow, for example. So we also thought about Earth as an exoplanet in terms of its rotational period. So if we could imagine having a great telescope with collecting enough photons, this is showing you the reflectivity of Earth, somewhat arbitrary units, as a function of time and days. So this is rotating over one day. And the curves are showing you, this is just a simulation showing you different wavelengths. But if there's no clouds, the ocean is very dark, and as land rotates into view, especially the Sahara Desert, because sand is very bright, you literally could see variation. With clouds, this ends up being about 20%, and it turns out our cloud patterns are somewhat stable enough to actually, we can't say like a map of the planet, but we would know that there's high contrasting materials in terms of their albedo or their reflectivity on the planet. On the right here at the bottom, I'm showing you an inference from real data. There was a spacecraft it was called Deep Impact. It got renamed Epoxy. It visited one comet, then it went on its way to another comet. And a group I was involved with got to command the spacecraft, and we looked back at Earth a few times, Earth as an exoplanet, and looked at I'm not showing you the light curve, something like this simulated one. And Nick Cowan, who led this work, extracted this map. I mean, this looks crude to you, but if we got this for an exo-Earth, it would be like, wow, totally amazing. We could see a sort of from the disk integrated light curve, we could get this crude longitude resolution. We might be able to infer there are continents and oceans, unless we can think about two other highly contrasting materials like that. So during the time when this work was done, just before this work from the one on the left from 2001, as Dimitar mentioned, I did my PhD here. I love to say last century, because I got my PhD in 1999. Newly minted PhD, I went to the Institute for Advanced Study in Princeton to work as a postdoc. And it was really cool to be like a domain expert, because no one really worked on exoplanets at the time, very few. But to my huge surprise, there was a newly formed group working on exo-Earths, because NASA had just started. Apparently punctuated over the decades, there have been studies on how would we find another Earth. And they had just started one that somehow coincided with my arrival. And David Spergel was leading the academic group there, but it was part of Ball Aerospace, a much larger group. And NASA had sponsored 4 different groups to sort of rethink how might we find another Earth. And long story short, NASA ended up choosing one and pumping in $50 million a year to get a telescope ready that could find another Earth. And this was back in the early 2000s. So in fact, it wasn't just one telescope. They wanted to have 2, one in the infrared and one in the optical. Because, by the way, when it comes time for us to see this dot, are we going to know the planet mass or size? We're not actually, because we're just measuring a brightness. In fact, it's the brightness and size combined that we're measuring. We don't know the size, so we don't know how bright it is. So for example, it could be a very dark large object or an incredibly bright small object. But if we could also get an infrared measurement, that kind of combines size and temperature. So if we can get infrared and optical, we could solve for the size, and then we would also break the degeneracy. And this is how people study like Kuiper belt objects, visible and infrared. Like that's pretty insane, that money and all that. And then eventually, I don't know, the powers that be realized how hard the problem was. The telescope had 500 terms in the error budget. It was too complicated, and the project was shelved pretty suddenly, actually. That's my memory, could be slightly wrong. So we still kept working on this project, but we still kept working on like Earth as an exoplanet, but this kind of cottage industry died down a little bit. So that's the introduction. What is another Earth? I think each person may have his or her own definition. It's, to me, an Earth-sized planet in an Earth-like orbit about a sun-like star, a planet with a thin atmosphere, with water vapor indicating liquid water oceans, carbon dioxide, possibly oxygen and ozone, and a planet with oceans and continents, which we may or may not be able to infer. So, right, I just felt obligated to show you this plot so I don't focus just on Earth. But there's so many planets out there. This is just a subset of them. Every point is a planet, and this is on a log scale. So, wow, exoplanets fall in such a huge range of mass, orbit, and everything else, really. So I showed this plot before and talked about it, but for today, the main point is that Earth here looks like it's close to these other points, but actually it's quite far from any of the points that could detect atmospheres. It's a log plot. We're not there yet with all of our techniques, and we need a technique where we can be able to measure the atmosphere so we can identify it as Earth. And I don't have time to do it justice, but actually I do teach a class on exoplanets, and I wanted to just let you know it's a very pedagogical, you can teach it in a way that you derive everything from first principles, as long as you might ignore eccentricity and some other slightly complicated things. All the methods for planet finding. Well, we don't do general relativity, but we do derive all these equations, and we can look at lots and lots of real data of planets and also try to gain some intuition about the discovery methods. So just like in my first lecture, since I don't have time to do the physics justice, I brought a copy of this book I edited, which has, I don't know, probably has a few thousand equations, maybe not, yeah. So best student question, please ask a question, and the book is for you. So continuing this introduction, I wanted you to know that an Earth, let's say an Earth at 10, 20, 30 light years away, it's not incredibly faint, like not fainter than the faintest galaxies ever observed by Hubble. The problem is the Earth, another Earth, would be right next to a big, bright, massive sun. And the problem is it's so close that it's very difficult to detect with any technique. Some of the techniques like that involve radius or mass, we can't see the planet directly, but rather its influence on the star. So if you were going to work on exoplanets, let's say you're going to take a sabbatical or you're a student starting out, which method would you choose? Would you choose a method that involves size? Because our Earth is 100 times smaller than our sun. It is 10,000 times smaller in area. So that means you have to be able to use a method that you can do to 4 decimal places. Would you use a method to find an Earth that relates to the Earth's mass, to its gravitational influence on the host star? Then our Earth is 300,000 times less massive. Or would you choose the method that, the hardest one, because our Earth is 10 billion times fainter than our sun in reflected light? So I just see it's hard with the masks to know what you're all thinking. I also love to ask the audience, do any of you work on anything where you have to make a measurement good to 10 decimal places? Once in a while someone says yes, but not too often. Well, if you want to pick the first one, that's the way we find most planets today, transiting planets. They go in front of the star as seen from our view. And on the top is a cartoon, the bottom is what we're looking for. We're looking for the measurement of the a brightness time series, if you will, to look for a tiny drop in brightness that might be a planet. I just wanted to share briefly with you, because I didn't have time to cover it in my other lectures, that we have a mission. The kind of main game in town for finding planets right now is TESS, Transiting Exoplanet Survey Satellite. It's an MIT-led NASA mission. Harvard Smithsonian Center for Astrophysics plays a big role because they're responsible for following up the objects. What you're seeing here is that TESS has 4 identical cameras. Each of them have an incredibly wide field of view, 24 by 24 degrees. And TESS looks at one giant strip of the sky. It's actually 24 by 96 degrees. For a whole month, it'll stare at that part of the sky, taking images pretty often, but they have to get binned on board because we can't downlink all of our data. And so what happens next is TESS stares at each patch for about a month and tiles one hemisphere at a time. And TESS launched on April 2018. It completed its prime mission, which was just looking at the northern night sky and then the southern night sky, and is now keeping going. So that's the TESS mission, and just to let you know how big it is, if you're familiar with the constellation Orion, Orion would fit within one TESS camera. So how do we find planets by this transit method? I made a few notes here for you in case you were interested, but I'm summarizing about 15 years of work in this one slide. So we want to have a star brightness time series. Computers actually find the centroid of each star on the image, and they plop like a circle or a special shape around to count up the brightness of each star. And they do that frame by frame. So computers construct a time series of brightness of each star. Computers detrend the data. And there's a lot there because we usually don't know the physical cause of any given trend in the data. We usually just remove it. And computers then search for a transit-like signal, rejecting false positives where possible. So there's lots of stars. There's 20,000 2-minute cadence per month postage stamps. There's like 1 million stars with a longer duration binning that come down. But literally think about that, millions of stars per month possibly for our computers to search through. And when the computers are finished doing all this, they usually spit out a few hundred objects per month that we actually use a human team, like a human crowdsourcing with experts. Here's a team from earlier on. Human vetters, we call them, group vetting, we call it, sort through the rest by visually inspecting light curves. And we have many auxiliary data products as well. So the computer spits out like a 1-pager, a few pager, and like a 50 to 100 pager. So you can always go back and look at the raw data. We can look and see if the star is moving around, if there's likely to be a false positive. And I just wanted to give you that snapshot. And for any undergraduates, TESS is a great project to work on because it's mature in the methods and it's an easy thing to start research on. So we have lots of these, and it's amazing to say that we find 100 new, we call them TESS objects a month, planet candidates. And I was chatting with some students earlier. We were talking about the spirit of Harvard research and MIT. You want to work at the frontier and do something brand new. And it was sort of a crazy world to live in today. When we say, well, planet finding, like with the transit method, it's not new actually. Like it's a crazy world when you say it's very standard to just find a new planet. It still takes a lot of hours, but it's not, this is a very mature field. So before, I also talked to you about the difference between finding a transit around a sunlight-sized star versus an Earth-sized, versus a small red dwarf star. And TESS, by the way, can't find another Earth. But I wanted to rehash this idea, this theme, that exoplanet astronomers are fixated on small red dwarf planets. And I put some numbers here for comparison. So the planet-to-star area ratio for Earth versus Sun is 1 part in 10,000. For an Earth-sized planet transiting a small red dwarf star, it can be as good as 1 part in 100. So there's a big difference in making a measurement to 1 part in 100 versus 1 part in 10,000. The probability to transit scales as the radius of the star compared to the semi-major axis. So for a planet that we want to find a planet that's temperate, that has a surface temperature similar to Earth's that we can estimate, the probability to transit could be about 1 in 30. Whereas for an Earth-Sun analog, it's 1 part in 200. We need to see repeat transits to know that it's period and to gain signal by binning data. For a planet transiting a red dwarf star in the so-called habitable zone, that's 1 week to 1 month. But for our sun, that would be a year. So TESS is built to be red sensitive, and it can capture small planets transiting small stars, but Earths are out of reach. Ask me about, if we have time in the Q&A, I can tell you how we want to find transiting Earths around the nearest brightest sun-like stars with a constellation of small telescopes. But for now, I did want to talk about something else. And if you haven't seen lecture 1, I do urge you to go back and look at the clip where I explain how the planets orbiting red dwarf stars are very different. They're tidally locked. The star, or the sun, is in the same place in the sky at all times. And the flares, the crazy flares that can be incredibly energetic. So the way I think about I just wanted to share the way I think about the planet around the red dwarf star. I think of it like an Earth cousin. So I want you to imagine you've gone on 23andMe, which probably most of you, a large number of you probably have. Imagine you go on there and it tells you have a cousin. Well, this cousin is like from a different country, speaks a different language, is like a different generation. That actually happened to me, by the way. It almost happened twice. Yeah, and one time it ended up, this is maybe a reason not to go on 23andMe. If you find out that someone in your family had an affair and produced a child that no one knew about. And so I do have this new aunt. She's a different generation, but she does speak the same language because she's in the UK. So now I want you to imagine for a moment, it's less likely, very unlikely of course, but you go on 23andMe and wow, it's not a cousin, you have a twin. Like, how would you feel about that? So that's how I feel about the Earth twin. Like, the Earth cousin is great, we want to know about it, but the Earth twin is something we're driven to find. And it would certainly help us in context. Because in the earlier lectures, I explained how, wow, exoplanets, we have so many free parameters, we're really just all over the place. So transits are only the first part of a long story. They're limited to planetary systems with a fortuitous alignment. And saying that another way, an Earth transit is rare. So we need a different method to go forward to enable us to find planets like Earth, to identify them to be like Earth. And that's the next part of my talk, possibilities. So we have this field, we call it direct imaging, because we're going to get a direct image of the planet. But remember, you're not thinking of that Apollo image of Earth. Image in this case just means the point source. Question?
Yeah, I have a question about the red dwarf.
Yes.
I mean, if I remember correctly, there's a lot more red dwarfs than there are these main sequence stars like the sun.
That's right.
Is there an argument about why Earth should be around a less likely type of star?
There is not.
Please repeat the question.
All right, I keep forgetting and you keep asking me to, so thank you for reminding me about that. The question was, there are so many more. The question is, there are many more small red dwarf stars compared to sun-like stars. Is there any reason why we should have Earths around a less common type of star? We're still sorting all of that out. It turns out that these small stars, they usually have small planets, and giant planets like Jupiter are rare around the small stars. That's as far as we've got. Because remember, it's hard to find small planets around sun-sized stars, but there do appear to be a lot of them. We haven't reached out to Earth's distance yet. Yeah, so there's no reason, but we can determine that empirically with time.
I was imagining there might be something related to the way the stars form and whether they have planets around the star could be a first generation star.
The question is, yeah, it may have to do with how the star forms. It probably relates to the mass in the disk. That's probably what it relates to. So I'm going to talk to you about direct imaging now, and I want you to imagining blocking out starlight so we can see planets directly. That's at the heart of this concept of direct imaging. Because remember, the planet is very close to the star, and for an Earth sun, the sun being 10 billion times brighter than the Earth, this is a real problem because we don't have that dynamic range in our detectors. So we've got to block out the starlight so we can image that planet directly. So you're all aware that if we have imagine a giant circular screen in space, and we want to block out the starlight so we can see the planet directly, well, the star is a point source. And what happens with a point source is you'll get airy rings because light can act like a wave and diffract around the edges. So up here I have a circle, and this is showing you airy rings. It's on a logarithmic scale because otherwise it didn't show up very well. And it turns out, the first ring is something like 100,000 times brighter than the Earth you would be looking for. So we can't have that problem. There is a way to re-engineer the diffraction. If you want to imagine a very special shape like this, what happens is the light can block out the point source, and it will diffract around the edges in a way that ends up with the image being very dark. You can control how dark it is depending on how well you can engineer that star shape. And the center would be so dark. And the analogy I really like is like dropping a pebble in a pond where you will see ripples. But imagine dropping a pebble in a pond, and all of a sudden the water is perfectly smooth. And all the waves are pushed to the outer edges. So my favorite concept in this whole entire field is called Starshade. You can imagine a telescope and the screen launching together. The petals can unfurl from their stowed position, with this truss now opening and the petals snapping into place. This starshade would be tens of meters in diameter, and it would formation fly tens of thousands of kilometers from the telescope to control the diffracted light. And this starshade, it has to be very precisely. There's a lot of complications with it. And here it is blocking out the starlight, and there happen to be 2 Earths there. Does anyone want to guess what this is? This is a 1% scale model of the starshade. So think for a moment how big that starshade, I said tens of meters, but let's see, who wants to guess how wide this is? I actually didn't measure it. Let's call it a foot, just for argument's sake. So if this is 1% scale, I'm giving you a really easy problem. How big would this starshade be at full scale? 100 feet in diameter. Very big. This starshade was used in the desert in Death Valley. And Northrop Grumman Corporation had a program to design the actual starshade as well as do this testing to demonstrate that it worked. It's not something we have in our astronomers toolkit. They got to something like 10 to the 7, 10 to the 8 contrast. They had a LED bank with a star and fake planets, and a camera, and the starshade went in the middle, spread over a few kilometers. But it was like dusty and there was turbulence. It was hard to get where they needed to go. Starshade, by the way, it actually was first, let's call it invented, in the 1960s by Lyman Spitzer. And he actually realized that to block out the starlight, because of diffraction, he would need to have an apodized screen so that it goes from like opaque to transparent, but very, very gradually. But that isn't as really buildable. And he worked out the math and found out that he could have like this binary, if you will, like on-off. He could have the star shape instead of an apodized screen. So and I seem to remember like it was because Lyman Spitzer and John Bacall as well got the Hubble Space Telescope up. So somehow I think this was associated with Hubble. But Hubble is orbiting in Earth's gravity. Earth's gravity is bad for formation flying. So Starshade would have its own spacecraft, and it would formation fly with a telescope dedicated to this. So the Starshade is a real thing. It doesn't have money to launch, not yet anyway. But there's been a lot of technology development going on for a long time. And yeah, I don't know I wanted to share this story with you because it's just such an unusual project when I first heard about it. This was back in the days when NASA was spending the $50 million a year. And I was involved with the program, as I mentioned. And I was at a meeting, maybe it was like the big astronomy meeting every January. And some of us got invited to like this private tiny meeting. There were like 5 people. And one of the people was John Ehrenberg. He played a big role in the James Webb Space Telescope. And he was like almost jumping up and down with his colleague, and Webster Cash, who helped reinvigorate the Starshade, was there. It turns out that this John Ehrenberg is from Northrop Grumman Corporation. We had to infer, we didn't know why, but he's building some kind of large deployables in space, and he felt that Starshade was very, very doable. Then it came time for someone to communicate that to like the larger community, the teams that NASA was spending all this money on. And I just want to recount it for you because there's some things like through your life you'll never forget. And this one was a meeting where everyone was really, truly paying attention. It's so hard to focus, right? Especially after the pandemic, and now we're trying to go to lectures in person, or you're on Zoom, and your mind is wandering. But every single person, you could have heard a pin drop when one of the people was explaining what Starshade was and how they thought that it was actually buildable. It was a defining moment for a lot of people. But because NASA canceled, remember, they turned off the flow, the project just kind of limped along for a while. And now the goal is to be ready for a possible mission opportunity later in the decade. And I just listed a few things. You can ask me later. People have masks on, as I was saying, so I can't see if people are like incredulous or they like this idea or what people are thinking. But most of this work now is happening out of Jet Propulsion Laboratory, a NASA center in California. Northrop Grumman is also working on it. This is just a picture showing you the Starshade lab. Membrane management, how to fold it up and how it will deploy. There's some scale models here and some older petals. By the way, I forgot to mention this petal. It's hard for you to see, but it has some very bright dots on it. And it goes on a table with a metrology system above it that has lasers that go zip, zip, zip all around, because this is a petal prototype used for manufacturing tolerance verification tests. That means these petals have to be made very precisely. You have to be able to manufacture it, to like it has to be, it's like 100 micron tolerance. So how do you test that? Like, how do you know if you've built something to 6 decimal places to 4 decimal places, that matches your design? You have to be able to measure it really well. And that's why this particular petal was made. That's myself and 2 team members. So that's Starshade. There's just a lot of different scale models, industries involved. It got somewhat popular. I don't know how popular it got, but it made it to popular culture, to this band who had an album. So there's another way to block out starlight that's also in the works, and it's called the coronagraph. And I'm showing you this beautiful image of a solar eclipse. And this coronagraph comes from Loeb, a French optical physicist who wanted to be able to observe our sun's corona even when there wasn't an eclipse. And he invented a way by putting a light blocking device inside the telescope in order to do this. And today people use coronagraphs, and I thought I would just spend a moment with this schematic for you about this so-called Loeb coronagraph. So from left to right here, it's showing you a telescope pupil, like the entrance to the telescope or the mirror, evenly illuminated, but it might have a secondary mirror that blocks a bit of light out. But for our purposes, the light comes to a focus, where the coronagraph involves what's called an occulting spot. So just like a little circle, tiny, that blocks out the starlight. But remember what happens, we would see airy rings. And so in this particular case, this focal plane is this focal image is re-imaged, and another stop called the Loeb stop would go in. Like, it looks like a miniature washer, blocking out some of those rings, those outer rings. And it's just showing you a picture here. It's not that great of a graphic, but it says the final image after the coronagraph has only 1.5% of the original starlight in this particular setup. We have to do way better, and there's like hundreds of different types of coronagraph designs. Like, there's a giant family of math, and it could be put at the pupil plane or the image plane, or there's a lot going on. But one of the main points is that the wavefront, the light coming in that hits the coronagraph, has to be nearly perfect. So any imperfections anywhere in the telescope will like destroy this method. And so it ends up that your telescope has to be very well thermal controlled. It can't be like vibrating. And you need adaptive optics, a way to sense and control to correct the wavefront so it's good enough to go inside. And so the coronagraph telescope in space that could reach down to 1 part to 10 billion, it has to be like so exquisite and perfect. And it's one of the challenges in this field. Starshade has its own set of challenges. You'd have to have its own spacecraft. Starshade has to retarget, like move across the sky to line up with each star. And it might have 60 total, 60, enough fuel for 60 different maneuvers. So it's not going to last forever. So each method has its benefits. I just had this crazy plot. So many coronagraph designs, too little time. But if you're interested in this field, I do encourage you to just browse it, look for some papers, because there's a lot of different options. So I'm now going to step you through where we're now and where we're going, and tell you about some of the possibilities. So this is plot, these types of plots in this community, we try to get them right and show them over and over. So I put a little credit down to the people who mostly making these lines here, which I'll explain in a moment. This is showing you flux ratio, the planet to star flux ratio. So for an Earth, it's 1 part in 10 billion, a seemingly impossible number. We have Jupiter here, not much better. And then up here, there are some objects directly imaged young planets that are quite far from the star. The bottom is showing you separation in arc seconds. People who aren't familiar with that term, think about 1 degree on the sky can be divided into 60 arc minutes, and each arc minute can be split into 60 arc seconds. It's a tiny amount. When we think of Jupiter and Earth here, we're thinking of a system at 10 parsecs distance, which is about 30 light years away. And this is showing you what we can do today with these points up here. We have a long way to go. And these curves here are what the telescopes can do. So there's the very large telescope sphere, that's European Southern Observatory in Chile. There's Gemini Planet Imager, that's on an 8-meter telescope also in Chile. There's something for Hubble. So what it's trying to show to you is that, far from the star, like as separated on the sky, it's a lot easier to image something, but as you get closer to the star, it's the diffracted light, even with a coronagraph, it's depleted, but it gets in your way. So hopefully everyone's with me. We can do really well today, like 1 part in 100,000, but we need to do way better. So today we can do ground-based telescopes with special instruments, can find planets, but they're planets that are self-luminous. They're still young, they have heat energy left over from gravitational potential energy that's still leaking out. We have these fantastic large ground-based telescopes now under construction, and Harvard is part of one of those, the Giant Magellan Telescope. They're going to work somewhere in this giant block here. So they will be able to have instruments with coronagraphs that can block out starlight, and they can get down to what it shows here, between 10 to the minus 7, 10 to the minus 8. And this actually works for those so-called Earth cousins, for finding and imaging in the near infrared planets in the so-called habitable zone of red dwarf stars. That's pretty nice, actually. I put a giant P here for Proxima Centauri, our nearest star, which has an Earth-mass planet in the so-called habitable zone. That's pretty awesome, right? We have at least one object that we can study when we get the right instruments and when these telescopes are online. By the way, it's sort of interesting to ask, why can't these telescopes do better? And as far as I know, you know what the reason is there's not a bright enough star. They can't sense and control the wavefront well enough to get down, to be able to control that wavefront to get down to the contrast needed, actually. And you might know, if you know about astronomy, you might say, why don't you just make an artificial guide star? Because your laser would have to be so powerful and expensive, it wouldn't be worth it, actually. So let's keep going down the scale here. We have a new telescope that's supposed to come after the James Webb. It's called the Nancy Grace Roman Telescope, formerly called W-FIRST. It has a kind of tech demo called CGI, a coronagraph instrument. And yeah, there's a separate mission we wanted to get flown with this. So I told you how the whole project, Terrestrial Planet Finder, 50 million a year, got canceled. Well, sometime later, maybe like, 7, 8, or 9 years later, NASA wanted to again restart the space-based direct imaging concepts. And they first, I think, wanted to call it Reduced Scope Terrestrial Planet Finder. But you don't want to call anything reduced scope, it's just not very good. So they renamed it Probe Class, which were to be direct imaging with a target of 1 billion. Now 1 billion sounds like a huge amount of money, but in space everything costs like at least 100 times more than on the ground. So it's not really that much. And so not having had like a group activity for a long time, I was very privileged to get to lead the Starshade. Now I suspect, like reading between the lines, that NASA wanted to just have a way to shelve the Starshade, to like kind of kill it forever. And that's fine, right? Because you want to know what your options are. And if something's too complicated and expensive, no need to pursue it further. So I think that because every time I would bump into the NASA leaders or go to NASA headquarters, it's like, they kind of seemed like they were like walking the other way. But we had a great time on this project. We brought all the threads, the technology, the science, everything that was happening together. We had enough funding to have like a team of engineers at JPL work it forward. And for anyone in this business, the wonderful thing was we always have to have a risk and cost assessment. Usually it's like blind, it happens after. But then you have no way to talk. But we had this risk and cost assessment ongoing. It was with Aerospace Corporation. So they hammered away at us at problems we had. And we came up with a great concept. And what our concept was that we called it Starshade Rendezvous Mission. Starshade would be built and have a spacecraft and launched separately from hopefully the Roman Space Telescope. So we could save a lot of money because we don't have to buy our telescope, it would already exist. And the Roman telescope only would have to have, be able to communicate with Starshade for formation flying, it would have to have a guide camera, et cetera, et cetera. I think unfortunately that, that ship, it might be too late for that now because time went on and the telescope had to move forward without all of its readiness. And its tech demo instrument, it's not really good enough. Like imagine having the most exquisitely possibly built Starshade, but it doesn't have a great science instrument to go with it. So this is kind of somewhat still unfolding, but Starshade Rendezvous, we'd be able to look at the nearest 8 to 12 sun-like stars and hammer away at them and see what's there. And for the most favorable candidates, we'd be able to get a spectrum of an Earth. Well, the story keeps going, actually. And there are powerful starlight suppression missions that, starting in 2016, NASA put out to be studied. And one of them is called HABEX, Habitable Exoplanet Observatory, a 4-meter telescope with a 4-meter diameter mirror, with a coronagraph and a starshade. Because the coronagraph is very efficient at zipping around from star to star looking for planets, but the chronograph's throughput is terrible. And it can only do this very fancy wavefront sensing and control at a very narrow bandwidth. So the idea is to find the planets with the coronagraph, and then Starshade is very good at blocking out starlight. There's no throughput issues on the Starshade itself. And so the Starshade would move around and get a gorgeous spectrum of the planet once found. And I'm just showing you here this sort of populated diagram that if we can do these missions, it would be fantastic. Look at all the planets we could get right down to 10 to the minus 10 and below, and this would be amazing. Now, anyone want to guess the price tag on this? I said the Starshade itself that would go with Rendezvous would be about $1 billion. We came in, I want to say, at like $7.5 billion. And something really big in astronomy is happening tomorrow. That's November, just for the online people who are watching the recording, that's November 4th. And that is that, I'm not going to say our fate will be sealed, because it's not quite that dramatic, but the Astronomy and Astrophysics Decadal Survey that comes out every decade by astronomers who get together and they create a priority rank ordered list of missions on the ground and in space of what should go forward. And Congress actually directs NASA and government agencies to follow this, like not to the letter. And the committee supposedly, I just learned this, they can't come back and say we want all these wonderful things when the budget won't allow it. Congress then can't come up with all that money. So it has to be cognizant of the budget and just surrounding and this and that. I'm not on the committee, being excluded for conflict of interest. I was also a co-lead of the HABEX study. So, if I was giving this talk to you tomorrow at this time, it might be very different. So it's one of two outcomes. Either HABEX gets like a #1 position, or if Starshade Rendezvous probes are recommended and Starshade Rendezvous gets #1 there, then it's a go, and it would still take us until the mid-2030s to be able to launch HABEX. Okay, so we're now at 2021. So call that like 15 years, and things always slide, so 20 years. So if they come back and say, okay, we're not ready to pay all that money, but we want to healthily fund technology development, then this mission decision is pushed another 10 years, and it's now going to be in the 2040s. So I just wanted to put that. Some people are smiling if you're like older, but the people who should be really excited are the young undergrads, because this will be your mission. Just like the James Webb is launching now, and people started working on this 30 years ago and over the last few decades, in astronomy, these things do take a lot of time. So I really like to say that all roads lead to terrestrial planet finder. It will happen someday, and let's talk about what it could get us. These are some simulations from the HABEX study. You're seeing a beautiful, it is actually a stunning image of a bunch of point sources here. Starting from the outside is like an enhanced Kuiper belt. In our planet, in our solar system, we have where Pluto lives, there's a belt of icy objects, and they also collide and make dust. In the very inside here, can you see a little weird looking blob? That's actually zodiacal dust. In this fake system, there's an asteroid belt with asteroids colliding and generating dust. And there's A, B, C, and D here. It's kind of hard to see A. That's what I was saying, is that Actually, I have to put my glasses are down there, but I have to put my glasses on to be able to see it. But it's tricky, right? Because it could be embedded in zodiacal dust. We don't know how much dust other systems might have. It's right there, probably hard to see, peeking out against the edge of that dust. And then B, C, D, and E are other planets in the system. So HabEx would observe the 50 sun-like stars and could find these and could also get spectra of them. And I'm not going to dwell too much on this. It's just sort of eye candy to show you that each of these with a lot more time. So let's say it takes hours or a day to find the planets. It would take like a week or more, to get spectra. But let's focus on the simulated Earth spectrum. So you probably don't remember in your mind what I showed you about our Earthshine. But this is like a simulated Earth, as seen by this studied HabEx concept with the Starshade. So for 370 hours, this is what you get. First of all, HabEx would be designed, okay, this is planet to star flux ratio times 10 to the 10, and this is wavelength in microns. These points with error bars are the simulated data, and then this histogram is just, I guess, a fit to the data. What you see from the left here is this ozone cutoff. Ozone in our atmosphere, you always hear how it protects us from high energy particles. It's such a strong absorber, and it just literally absorbs everything. That would be amazing if we could see this, because ozone is a byproduct, photochemical byproduct of oxygen. And here you also see a big ozone feature. There's, as we saw before, oxygen, there's water, and this would be like a fantastic spectrum. So based on the last two lectures, I was wondering, I would just love to chat with you about how you feel about this. So wow, we find an Earth twin. I mean, this is an Earth twin by design, and I made a little note here. The team modeled many other possible terrestrial planet atmospheres. We're just showing you Earth because today's lecture is about Earth as an exoplanet. But if we had this, it would be more exciting than anything possible in this field. We'd have oxygen and water and ozone. We haven't quite picked out anything else, carbon dioxide or methane, but I'm just curious if anyone here would be thinking, wow, we found life elsewhere. The answer is no, based on what we were talking about the last couple of days, okay? Because we can't prove anything here. We don't have context. We don't know a lot about an exo-Earth. We have the dot and the spectrum. Maybe we can get a mass from another way. So although it would be a triumph, the story would keep going. And I do have a couple more slides here. And I really wanted to tell you a bit about ideas for the future. So in exoplanets, the line between what is mainstream and what is considered crazy is constantly shifting. When Dimitar and I first started on exoplanets, there was a lot of pushback. It was considered, maybe not here at Harvard, but in general, not worthwhile, waste of time. There was a lot of other angry stuff going on that I was shielded from, thanks to Dimitar. But in general, when I started leading the Starshade project, I would tell people about it, even at a barbecue here out in Harvard, Mass. And people were like, what? Starshade? That's dead. That never would work. And they'd have their list of reasons. And so now I told you about Starshade. No one, maybe you were opposed to it, but no one looked incredulous. So it's hard with the masks. It's a small audience. So I had to do something that might seem incredulous to you. I wanted to demonstrate it is really extreme. And the question is, how can we do better than that spectrum? How can we do better than HabEx and LUVOIR that are very complicated and still a few decades out? A little typo there. Well, there is this amazing project. I'm not involved with this in any way, but this plan is to actually send thousands of tiny spacecraft zooming by the nearest planetary system. And this idea is to send up, it's like the turtles that are born and they're not all going to make it. There's lots and lots of little babies. They go out to the ocean. It's like sending out a lot of these things. They're not all going to make it. But the idea is it's called Starshot. And the idea is to send up space chips. Instead of a spaceship, it's a space chip. A chip that goes up there, but also has a solar sail. So it'll deploy a few meter in diameter solar sail that will have to get accelerated by a giant bank of coherent lasers. You can see focused by these telescopes. This would take up literally a square kilometer of land and be 100 gigawatt power. And this idea would be to accelerate these little sails to 0.2, a 20th the speed of light. And if you could do that, accelerate them without blading them or getting permission to not destroy any for airspace and everything.
speed of light.
Then they would still take a long time, 20 years, to get to the nearest star system. So this project is being funded by the Breakthrough Initiatives with $100 million to buy down some of the technology. So whether this happens, whether it's too crazy, like just putting the money down and like planting the seed that someday we'd like to be able to go out there is a big deal. Okay, so I don't know how well that came across, but these things would go out there, they would snap an image as they're zooming by, eventually transmit that image back to Earth, and we would have a snapshot of the planet. Second idea is what's called the Solar Gravitational Lens Telescope. And this idea is to magnify an exoplanet by billions of times to get down to like kilometer scale resolution. And here the idea is that we would use our sun as a gravitational lens. We'd have to send spacecraft to 500 astronomical units. And these spacecraft would have to block out the starlight, and you'd have to know where your target is. So you'd purposely send it in a specific direction to use the sun to magnify a background planet. This one's really hard to do because you have to slingshot around the sun, get really close to the sun, and you'd have to get lined up just perfectly and take the images as you go along. This also is like at least 20, 30 years away, and it would take 20 years to get to its destination. So I'm just trying to impress upon you whether or not you think this is ever doable, that if we get the beautiful spectrum of another Earth, our job's not done. We have to hand it over to the next generation to think of how we're going to go further to find out whether or not the planet signal if we see water vapor and oxygen to really find out more, and whether we can infer that there is life on that other world. So I have two summary slides. The search for other Earths, we can divide that into two categories. One is transits. With the James Webb Space Telescope, atmospheres accessible for a handful of habitable zone planets transiting M-dwarf stars. We have some already. I just call that the Earth cousin, which will also be accessible by the ground-based extremely large telescopes. A few dozen red dwarf stars, we can survey those and search for planets, Earth cousin. And I've highlighted the one I talked about today, space required for finding Earth-like planets orbiting sun-like stars. So to summarize, biosignatures are gases produced by life that accumulate to detectable levels that are very out of equilibrium with their environment. And here I'm summarizing all three lectures. Water vapor is a good habitability indicator because all life as we know it needs liquid water, and atmospheric water vapor shouldn't be on a small rocky world unless there's a reservoir beneath it. We will likely have to have an informed, what we call some kind of probability for gases to be associated with life other than false positives, rather than being able to deliver wonderful news to you in the future that we've found signs of life for sure elsewhere. I talked about Venus, and the solar system objects came up. There's a growing list of intriguing potentially habitable planets and moons. But again, for robust detection in this particular case, we'd want to push for sample return. The generations-long search for life elsewhere beyond our own planet has already begun, and I wish you clear skies on your own journey of exploration. Thank you very much. And we have time for some questions, and we're also going to welcome some online questions as well.
Okay. I'll run up and down.
Get the microphone.
Thanks for a really nice talk. I just wanted to ask if there are any ideas for using something like polarization to get around this problem of the host star brightness when searching for exoplanets. I guess the idea I have in mind is that you have the light from the star being primarily unpolarized, and you might have some sort of polarization pattern from scattering off the atmosphere of an exoplanet.
Yes, it's a great idea. And people have tried to do this, by the way, with giant hot Jupiters close to the star that are orbiting the star, looking for a change in polarization due to the change in angles. And so it is a great idea. People love this idea. So thanks for bringing it up. But it's hard because polarization is so tiny, It's just like a few % of the signal to begin with. And it might reduce the planet-star contrast, but we still need to block out the starlight, and it ends up just lowering the signal so much. We'd like to do it, though, partly because it contains other information about the planet that might be useful.
Thank you.
Okay, hi. Thank you for the talk. It was really interesting. And I was just wondering, so if you're looking for an Earth-like planet specifically, would you expect that sort of planet to show up like as a single planet or as part of a multi-planetary system, given that like the solar system has multiple
Right, the question
planets?
is, if we find that Earth-like planet, would we expect it to be part of a solar system just like ours is, or by itself? Like usually when we want to make a guess, we're wrong. It turns out in like planet formation and what's out there. But I'd say there is growing evidence that, well, we like to believe that, not very scientific, and there is evidence in some cases that planetary systems are always multiple and they're usually full, that they're dynamically full. So you couldn't add more planets. In some cases, we don't see very many, but that's like a giant planet close to the star that might have moved inwards and gotten rid of all the other ones. So I would expect it to be a part of a planetary system, but not necessarily one like our own.
What's the schedule for the giant telescopes you talked about?
Let me think. I'm not sure exactly when it's coming online. Maybe Dimitar knows for the Giant Magellan Telescope. But while he might answer that, the giant telescopes here in the United States, they're also waiting for tomorrow because they need to they'll hopefully get ranked #1, which can unleash some funding. Like to my knowledge, they're not fully funded and they're waiting for a chunk of money to come from the government.
Yeah, everybody's waiting for tomorrow.
Thank you again for the nice lecture. I have two questions. The first one is a clarification on one of the plots that you showed both today and on Monday. But on the 2D chart where you have all the exoplanets, and then you superimpose the planets of the solar system. And basically, all of them are very far away from all the exoplanets that we've observed so far. And I'm wondering, is the bias of the fact that we haven't observed exoplanets like the one of our solar system is because the typical stars that we can see exoplanets around don't have planets that look like our solar system's planets, or is it because of the planets themselves?
That's a great question, and it's some of each, but we don't, the question, just to repeat it, was, I would ask it another way, is our solar system rare, or is it bias? And it's actually, it's a bit of both actually. So we know we're definitely biased to big planets close to the star, to any kind of planet close to the star. I had this sort of crude sketch of our bias for direct imaging. We're way up here. We can't get down to small, low mass planets. The other techniques are really shoved over. But I would say we don't have a great number, but the best number I can come up with for you, well, we know our solar system is not very common. It could be like 1% or 10%. It could be 10% or less. But we don't have a great number, but we know that they're not all like ours. Our solar system is incredibly hard to find. We might have one or two like Jupiters that are orbiting far from their star. You know, Jupiter takes 12 years to go around our sun, so you want to see that a couple times, it's 20 years. So yeah, we think that our solar system is somewhat rare.
And the second question is about the Starshade. So if I remember correctly, the diffraction has a dependence on the wavelength. And so I'm wondering if that structure works at specific wavelengths, or and if you want to do spectroscopy on a wide range of wavelengths, as you showed, like from microns to from UV to infrared, what's the deal?
Yeah, so it is a good question. We can design Starshade to cover very broad band, but then it ends up having to be bigger and further away from the telescope. So if you only wanted to look at short wavelengths, and you just want to find the planet and maybe look for the ozone cutoff, you could get a smaller Starshade closer to the star, but a bigger Starshade further away, designed in the right way, could cover a range of wavelengths. But it can't get us from UV all the way to near IR. We'd have to move the Starshade around.
Thank you very much for the amazing talk. And I had a question regarding the TRAPPIST-1 system that you mentioned earlier, and just red dwarfs in general, and what you think their potential for hosting habitable planets is, given that they have like strong stellar winds, but also like because they're so common and they're good candidates for direct imaging, it would be really exciting for them to be able to have habitable planets. So
So the TRAPPIST-1 planets, they're quite close to the star, and we won't be able to directly image because they're too close to the star. So I didn't explain the details. Like if this was my class, I could walk you through. We need to spatially separate the planet and star in the sky and block out the starlight. And the TRAPPIST planets, they're just too close to the stars projected on the sky that we can't see them with direct imaging. However, for transits, it's such a great question. And it's one that, fingers crossed, James Webb launches safely, we can answer empirically. So we might want to hold off. I can just say, yes, I think it does. I like to imagine the planet has a good reservoir of materials that will always outgas, so it will always have an atmosphere. I don't think flares will kill anything. Life could live beneath the surface. But I think that's we want to believe.
Thank you.
Well, that's great.
How about
one
one
more
last question right here?
One more question.
I was wondering if you could talk a little bit about the Copernicus constellation that you mentioned as a way of
Right,
detecting.
and I'll just say it very briefly because some people will want to leave it at the end of the hour, but thank you so much for asking that. I think that must have to be the best question. Okay, so when Terrestrial Planet Finder was canceled, the $15 million per year, I actually had just arrived at MIT and I had wanted to start something bigger that could last longer. And there's a joke that if you go to that MIT is engineers are us. So you end up at MIT and you end up learning some engineering. And so my idea was to have lots of little tiny telescopes. Now, of course, you all know about the mega constellations up there. But each telescope would look at one sun-like star, the brightest stars in the sky. They're spread all around the sky. So we can't look at them like just with one telescope because they're all around the sky. And to find a transiting Earth, we need to stare at the star for years, at least 2, probably 3 or more, with the exception of the sun and moon constraints. So I really have this idea. I love my idea, of course. It's not entirely practical for reasons I won't have time to get into, but there are so many stars and Earth transits are very rare. So we have to have a way to drop most of the stars. And if we make an assumption, which looks like it might be true for outer planets, that planets orbit in the plane of the star, and we can find out a way to measure the stellar inclination, we actually can rule out a lot of the stars if they're not inclined favorably. And so we want to use a technique called astroseismology, where sound waves in the star, it looks like it's got different modes of vibration, and that sort of breaks the 3D symmetry. So we actually could be able to gain its inclination, and we'd have to have a little telescope that could focus on each star. So if you'll just bear with me, I'll wrap up in a second, but so I got to MIT, I wanted to do this, I learned about CubeSats. I asked a colleague if I could incubate the project in his class and bring a science team to the class. And we did it, actually. We got this little tiny telescope. Oops. That's the class. I'll just tell you very briefly about this. Prototype. This isn't the constellation. The prototype, we got to be delivered as cargo to the International Space Station in 2017. In November of that year, our spacecraft deployed. This is before the solar panels open. You can see those are the big solar panels of the International Space Station. And what we wanted to do was just demonstrate that we could do precise stellar photometry. Because one thing I haven't told you in all of this is that the key to getting the precise brightness as a function of time is to point your telescope very precisely. So the centroid of the star is on the same fraction of a pixel at all time. Because if you were to, let's say, open your phone, that's probably a CMOS detector or CCD, and you shine a laser at it and measure the amount of light coming back, it varies by 40% over a pixel. So it's like, you have to be able to point very precisely, and to be able to point a small thing precisely is hard. Like a big thing has a lot of inertia and it's better, and even the reaction wheels on it couldn't. So we actually did figure out a way, like 10 years, I'm summarizing 10 years in 1 minute. We actually solved this problem. We launched our telescope. We managed to point sub-arc second, 100 times better than anything in its mass category. And we're now ready to move on to the next step to try to design and build a constellation. We've just run up on a snag because buying down risk is cost. And we went through a NASA costing model, which was cost prohibitive for the individual telescopes. So we have to wait to find a way to build things cheaper to make that program work.
Okay, so let's thank our speaker one more time and 3 times more for the 3 lectures. Thank you.
Thank you.